Hello students, welcome to Sri Jayendra's Ring Zone classes. I'm your friend and mentor for coming classes with respect to physics. This is lecture number 5 of a unit thermal properties of matter. So let's begin with today's class. In today's class we are going to discuss primarily about the transfer of heat. So when I say transfer of heat, we can say that heat is transferred from the higher temperature to a lower temperature region by three different processes. We have one of the process as a conduction, as the convection, and as the radiation. Now this diagram, this is very effective diagram which will let you know that what conduction is, what convection is, and what radiation is. Let's suppose this is the case of convection, that amount of energy has been transferred from the lower region to the higher region, and you're here, a person has kept his hand over here, and by such this amount and by in this manner, energy has been transferred from, let's say, from this is a source of energy, this is a source of energy to the hand of a person. I hope this is clear. So it is method of a convection. Now let's understood that, let's suppose you have one of the stick in your hand, and let's suppose you have touch it, you touch this stick to this flame, and you will feel that this end of the stick, let's suppose this stick is framed with the certain metallic element, then this is going to be heated. This is what we understand as conduction. And let's suppose you have kept your hand over here, this is what we call as a radiation. So what we are supposed to do is, according to the planning, we are going to cover convection first, then it would be the conduction, and then at last it would be the radiation. So let's begin with the convection first, how these things will behave and what would be the situation. Let's have a look. When we say convection, we mean that process of heat transfer from one place to another by actual movement of particle of medium due to difference in density. That is what we call as a convection. Mainly it is predominant in liquids. So convection is predominant in liquids. Mainly it is observed in the liquids, and we can say it's a rate of heat flow, which we can say it's a Q by T, which is directly proportional to the area A and the temperature difference delta theta. So I can say it's a P which is directly proportional to the A into delta theta, where A is the area and delta theta is the temperature difference. It's temperature difference. I hope this is clear. Yes, where A is the surface area over which fluid moves, and H is the coefficient of convection. Now when I discuss convection, we have two convection. One of them is the natural convection and another one is the forced convection. First let's look at the what natural convection is all about. It is transfer of heat due to the movement of the fluid resulting from the differences in density. That is what we call as a natural convection. Examples of natural convections are hot air rises by natural convection, a sea breeze could be there, a land breeze could be there, and many more examples could be there. Many more examples could be there which feels a natural convection. Let's look at this. When a vessel containing water is placed on a fire, then water is heated by natural convection. So in this situation, what the situation is, let me draw this and make you clear this, that this was the situation. This is just for the understanding purpose. Please take it and consider it in a manner such that this could be understood. That let's suppose I am going to heat up this water. If I'm going to heat up this water, let's suppose I have layers defined. This is first layer, this is second layer, this is third layer, and this is fourth layer of the water. So what happens initially this container is being heated, and when this container is being heated, very fast, layer 1 is going to be heated. As layer 1 is being heated, it will be the hotter region. When temperature of the layer 1 increases, so volume of layer 1 increases. But when volume increases, density decreases. So if density decreases, this layer will switch itself to this. So now the situation would be layer 2. Layer 2 would be at this position. Layer 3 would be at this position. Layer 4 would be at this position, and layer 1 would be at this position. Now again the same situation will be there with layer 2. It's a temperature of layer 2 increases. If its temperature increases, its volume increases. If its volume increases, its density decreases. So the situation is this, that this layer number 2 is going to shift itself to this position. Now the situation is the layer number 3 would be at this position, layer number 4 would be at this position, layer number 1 would be at this position, and layer number 2 would be at this position. Again again what we are supposed to do, it's the same cycle. It's a temperature of layer 3 increases, and when this temperature of layer 3 increases, their volume of the third layer is increases. When volume increases, its density decreases. If density decreases, that means fourth layer is having a higher density as compared to the third layer. So this layer 3 will shift itself to the upper layer. So now the situation is, it would be a 4 1 2 3. Again the situation will be the same. It's a temperature of fourth layer will increases. And when temperature of the fourth layer increases, that means its volume of fourth layer will decreases. If volume decreases, its density increases. So this density of fourth layer increases, and when its density increases, sorry, I made a mistake. Its volume will increase, and so that its density will decrease. So if this is the situation, a fourth layer will switch to this, and again you will have this parameter. It's a 1 2 3 4. So this is how natural convection behaves. This is how natural convection behaves. I hope this is clear. Is it clear? Is it? So this is how, when we put up water in a container and that container on a stove, this is how actual flow will begin, that you can see in this diagram as well. Yes. So this is what we call as a natural convection. This is natural convection. One more application of this is the sea breeze and land breeze. What will happen? Let's suppose, due to sunlight, this sunlight is available on both the region, on the land as well as on the water. But water is having a high specific heat capacity. So when water is having a high specific heat capacity, it requires or it takes larger amount of energy to get it warm. But land is having a lower specific heat capacity. I can say it's a C of a land will be less than C of a water. So what happens? This land will be warmer, and when this land will be warmer, the area which is connected with the land and air that remain in that area would be warmer. If they are warmer, they would be lighter in density. They would be lighter by weight. When they are lighter by weight, they will be moving in the upward direction. When this are moving in upward direction, here vacuum kind of thing can be created, and so that a breeze from the sea has been rushed towards this region. This is what we call as a sea breeze. In the night time, the situation will be exactly reverse. the situation will be as specific heat capacity of land is much smaller as compared to the specific heat capacity of water. So as land can become hotter easily, it could become a colder easily as well. So in this situation land will be colder, and water is probably is still at a hotter region. And if water is at still at a hotter region, the air over it moving in the upward direction, because it is less in density. If it is less in density, here vacuum kind of thing can be created, and so that air from land to water is going to be rush, and this is what we call as a land breeze. This has been taught to you in probably 6th, 7th, or maybe in 8th class also. How you remember this? Do you? Do you remember this? This is how natural convection works. Many practical applications are there. Many practical applications are there. I hope you must understand or you must remember which are the practical applications. The practical applications of convection. We install chimneys at the top side of the stove. Yes, I'm talking about the chimneys that we installed in our kitchens. Yes, that is already installed at the top side of the stoves. Why? Because whatever the hotter air would be there, why we are using the chimneys? So that it can suck all the hot air, and it can throw it away to the kitchen or throw it away to the home. So where do this all the hot airs will be available? At the top of the area of the stove. So we always install chimneys at the top of side of the stoves. Even you can understood this, that we install exhaust fans at top region of room. Yes, if you have seen the exhaust fans that is used to suck all the hot airs from that room to the outer region, we always install this at the top of the region. So this and many more applications are there of convections. So basically convection is predominantly done in liquid, but this is not happens only in liquid, this happens in fluids. I hope you understand the fluid. Fluid is the one which can flow. It could be liquid, it could be gases. I hope this is clear. So now let's back to the forced convections. It is transfer of heat due to the forced movement of the fluid by mechanical means, such as a fan could be there or a pump could be there. This is known as the forced convection. As we have discussed, ventilation in house is an example of the forced convection. Are you clear with this? Are you clear with this? So let's look at certain quick questions. Which of the following is an example of natural conduction? Yes, land breeze, sea breeze. Yes, this both are the examples of the natural conductions. Next, the forced convection of blood. The forced convection of blood in our body by the heart helps in keeping the blank of the body constant. Yes, it is there to keep the temperature of the body constant. I hope this is clear. Is it clear? So, do you have any doubts up till now? Do you have? Is there anything? Is there anything? No? Great. Now let's look at the conduction process, that how heat is being transferred using conduction process. Let's look. We can say the process of transmission of heat energy from one place to another without movement of the particle of the medium is known as the conduction. So here the particle of the medium is not going to transfer from one place to another, but without transformation they are going to transfer the heat energy. In this process, heat transport takes place by molecular vibrations. So let's suppose, look at the cases that, let's suppose this is one of the pen, and that pen has been connected on the heat source. And when I switch on this heat source, when I switch on the heat source, this pen gets heated. This kind of heat transfer can be considered as a conduction. So first let's understood that what is coefficient of thermal conductivity. So when I say in the steady state the temperature at any point of a slab or road that does not change as time passes, but this is the case of the steady state. But along the slab, or I can say road, from higher temperature to lower temperature, and temperature decreases from point to point. So let's understood the situation that this is one of the road, and this is connected with two different temperature on the two ends. One is the hot end and it is maintained at temperature T1, and the another is the temperature, another end is maintained at temperature T2. The length of the conductor, the length of the conductor is the D, and let's suppose we understand that, let's suppose the certain amount of energy is being passed from one end to another, and this energy being passed, this depends on certain factors. One of them, it's a cross sectional area, another it's a temperature difference that we call as a theta 1 minus theta 2, one more it's a t, and it is inversely proportional to the length. So if I look at this all this parameters, if I look at all this parameters, what I can have, it's a q by t, that is equals to k into a into bracket theta 1 minus theta 2 by L, while k is we call as a conductivity. Yes, it's an conductivity, or I should say it's a thermal conductivity of an object. So we can say the change in temperature with distance, it's a theta 1 minus theta 2 divided by d, that we call as a temperature gradient. When and when we divide anything with distance, that is what we call as a temperature gradient. So this temperature gradient can be written as, it's a theta 1 minus theta 2 divided by d, and this theta 1 minus theta 2, it's a Kelvin, divide by d, it's a meter inverse. So this dimensional formula of this could be written as L to the power minus 1 into K. I hope this is clear. Is it clear? So so now let's suppose look at the situation. Let's suppose look at the situation that this was the situation that we were discussing. This end is at temperature theta 1, this end temperature theta 2, this length d, and heat has been traveled from this to this. This heat is being traveled, that depends on the area of cross section, it depends on the temperature gradient. So if I write this heat current as a P, then it is directly proportional to the area of cross section, and it is always directly proportional to the theta 1 minus theta 2 by k d. This could be written as, if I remove the proportionality constant, this is k, where k into a into theta 1 minus theta 2 by d, or this k could be written as delta q by delta t, or it's 1 by a into bracket d into theta 1 minus theta 2. So you must remember this formula, and the other things will be done on its own. I hope this is clear. Yes, this is what we call as a thermal conductivity. Now, SI unit of thermal conductivity. SI unit of thermal conductivity, it's a watt per meter into Kelvin, because it is something like this. It's a Q by T, which is equals to K A T1 minus T2 divided by L. This Q by T, it's an watt. This area meter square, this L meter, it's a meter square by meter, so it would be a meter, and this T1 minus T2, that is Kelvin. Yes, so it's a joule per second, which is watt. It's a watt per meter into Kelvin. Dimensional formula of K, It's an m1 l1 t minus 3 k minus 1. In general situations, solids are better conductors than liquids and gases. For metals, K is an infinite, and for insulators, K is equals to 0. Copper is used at the bottom of cooking utensils because it is a good conductor of it, and it can transfer heat energy very effectively within no amount of time, almost 0 seconds. That's why the situation happens that if a steel spoon is there, or suppose a certain object is there which is made up of metal, and one end of that metallic slab or metallic rod or metallic spoon even, let's say, is connected with the source of an energy, then the other end gets warm instantly, and it took almost no second to get it done. I hope this is clear. Now let's look at certain the quick questions. Look at this carefully. SI unit of temperature gradient. This temperature gradient, this is dq. Sorry, it is a dt by dx. The temperature gradient that could be written as dt by dx, and this could be written as T1 minus T2 by L. So this is a Kelvin. This is a meter. It's a Kelvin per meter inverse. I hope this is clear. Second question. It says the amount of heat conducted through a metal rod is directly proportional to amount of heat conducted through a metal rod is directly proportional to, it is something like this. It's a delta q by delta t, which is directly proportional to the A into bracket T1 minus T2 divided by L. So it directly proportional to the area of cross section. Yes, this is correct. It directly proportional to the temperature gradient. Even this is correct. It directly proportional to the time of flow of it. So this everything is correct. So all of the above is the correct answer. Next, coefficient. Coefficient of thermal conductivity. It's an K. This depends upon the nature of the material of the body. Yes, this is absolutely correct. Is independent of the dimension. Yes, it is a materialistic property. This is a materialistic property and does not depend on the dimension of the body. K does changes if material changes. So if I have made, let's suppose this is very logical question. Let's suppose this two roads are there and both are made up of copper. As you can see, this both are having difference in their lengths. Let's say this that their cross sectional area even changes. This is A1, this is A2, but this two have a same conductivity. I'm talking about the thermal conductivity. Yes, so it is a materialistic property and it is not dependent on the dimensions. So this 1 and 2 is correct. Depends on temperature gradient. No, they are not depending on the temperature gradient. I hope this is clear. Is it clear? Is it? So does it clear up till now? Everything is clear. Now let's summarize this situation. Let's summarize this situation and work on the numerical. So we have said that this was the situation, that this is a metallic rod is there. This end is at T1, this end is at T2. This is the length of this rod, and this is the, let's say, cross sectional area of this rod. The amount of heat energy that is being passed, that we call as a Q by T, which is directly proportional to the cross sectional area, which is directly proportional to the temperature difference, and which is inversely proportional to the 1 by L. It's a 1 by length of the conductor. If I replace this with the proportionality symbol, then this could be written as Q by T is equals to K into A into bracket T1 minus T2 divided by L. This is Q by T, or this could be written as dq by dt, that is equals to minus of K into A into dt by dx. This is the same form. I have written it differently. This negative sign shows that it's a decrease in temperature. The negative sign shows that temperature is being decreased. That's why I have written it over the negative sign. So this is dt by dx, and this dt by dx could be written as temperature gradient. I hope this is clear. Yes, so this is first summary sheet, and on the second summary sheet they will say that in a steady state situation, in a steady state situation, when the thing will be of the steady state situation, I can have a two things. First, dq by dt of any segment will be equals to constant. This is a first part. So it means a net flow of, that means net flow of energy is 100%. That means no one is going to absorb something, everyone is there to transfer something. That's whatever amount of, let's suppose this is T1, this is T2. If I divide this segment in, if I divide this road into different segments and give it a number to the different segments, 1 2 3 4 5, and let's suppose this has received 100 joule of energy, then it will pass 100 joule of energy to the second. Even second segment will pass 100 joule of energy to the third. Even in the third segment it will pass on the fourth, 100 joule, 100 joule and 100 joule. So net flow of energy, net flow of energy is 100%. That means whatever you are going to receive, you are going to deliver it to your neighbor. This is the situation when I'm talking about the steady state situation. I hope this is clear. One more thing is, in steady state situation, dt by dx, dt by dx is always constant, temperature gradient is constant, that you understand. I hope this is clear. Is it clear? Is it clear? So are you ready with the questions? Are you ready? Can you do this? Are you sure? Great. Now let's work for the questions. So the question says that, let's suppose this is the situation, that this is one of the road, this is another road, this is at 100 degrees Celsius, this is at, let's say, 0 degrees Celsius. This temperature I want. Length of this, it's a 3 meter. Length of this, it's a, let's say, 2 meter. A cross sectional area is been not given, but this is A. The conductivity of this is, let's say, 2k, and the conductivity of this, it's a 3k. What they want, they want that find out temperature Tx at the junction. This is the requirement. Find out temperature Tx at the junction in steady state. So how will you do this? What I understood is that, let's consider this as a first segment and this as a second segment. If this is the situation, if this is the situation, then I could write it's a dq by dt of first segment is equals to dq by dt of second segment. So this is equals to k1 a1 t1 minus, for this segment this second temperature is Tx, divide by L1, that is equals to K2 A2 into bracket Tx minus T2 divide by L2. This will be the situation. So if I put up the value, it's a 2k multiplied by A multiplied by this T1, it's a 100 minus Tx divided by length, and the length would be equals to 3. That is equals to mm, let's write it on the second slide. No space would be there. So this could be written as that k1, it's a 2k sorry. So this could be written as 2k multiplied by cross sectional area A multiplied by T1, it's a 100 minus of Tx divided by length, and the length would be of 3 meter. That would be equals to 3k multiplied by cross sectional area into bracket tx minus 0 divide by length would be of 2 meter. So this k and k has gone, this a and a has gone. This is 2 2s are 4 into 100 minus tx. This is equals to 3 3s are 9 into tx, because this is tx minus 0. So this is 400 minus of 4 tx is equals to 9 tx, and this could be, it's a 400 is equals to 4 plus 9, this is 13 tx. So this tx is equals to 400 divided by 13 degrees Celsius. I hope this is clear. Is it clear? This is 400 by 13 degrees Celsius. Do you understand this? Are you sure? Are you sure? Any doubts? Is there anything? Is there? No? Let's move for the next question. Let's suppose the situation is something like this, that this is one of the route, and this end is at 100 degrees Celsius and this end is at 0 degrees Celsius. This length is of 10 meter. So they ask me that this is the tx and this is a 4 meter from this side. So they want that find out tx in steady state situation. So if I consider the steady state situation, I need to find out the temperature at this end. It is from the left end, it is at 4 meter. How will I do this? One of the situation is, look at this, they have said me at that it is a steady state situation, and if they said it's a steady state situation, if they mention that it is a steady state situation, I can equate the temperature gradient. So what I can do, it's a dt by dx of 1, this is equals to dt by dx of 2. This is the first segment, this is the second segment, and dt by dx of first segment, so this is 100, this is tx, it's an 100 minus tx divided by this length, it is of 4, that should be is equals to, this is tx, this is 0, so this is tx minus 0 divided by this length is of 6 meter, because total length is of 10 meter, so this is 6. So when I try to solve this, this is 100 minus tx divided by 2 is equals to tx by 3. So this would be 300 minus 3tx is equals to 2tx. So this is 300 is equals to 5tx, and from this tx is equals to 300 by 5, which is equals to 60 degrees Celsius. I hope this is clear. Is it clear? Is it clear? Are you sure? Are you sure? Yes, this is one of the approach. This is one of the approach. Let's work on the same question using second approach. So the situation is, it is something like this, that this road is there, and it is here at 100 degrees Celsius, here it is at 0 degrees Celsius, and this is at 10 meter. When this is at 10 meter and I need to calculate it over here, I need to calculate at this location. So what I understand is that tx could be written as t high minus dt by dx multiplied by length that they have been used. So this is equals to that th, this is equals to 100 minus dt by dx. So this is a difference of 100 degrees Celsius and 0 degrees Celsius. So basically it's a 100 minus 0 divided by total length, this is a length of 10 meter, multiplied by length that you want, it's a 4. So this tx could be written as, this is 100 minus 100 by 10, it's a 10 into 4, this is equals to 100 minus 40, this is plus 60 degrees Celsius. I hope this is clear. Is it clear? Is it? Are you sure? Do you understand this? Have you got this? Have you? Great. So now are you capable enough to do this kind of questions? Will you be? Are you sure? Are you sure? Great. Now let's work for the next question. Let's suppose understand that this is the situation that these three roads are there, and this is, let's say, temperature of 100 degrees Celsius, this is of 20 degrees Celsius, and this is of 30 degrees Celsius. The question says that all roads are made up from are made up from same material having same dimensions. Find out temperature at the junction. So this is the Tx. Now a same question has been asked by the advanced as well. JE Advanced has asked this. Only the difference is they have been made up from the different materials, so different K was there, and the dimensions were different. So it was just the calculation missed. It was just calculatively it was different. Otherwise, conceptually it was the same question. So let's look at this. A very good question is that what should I do? What I understand is that let's understood that this is at 100 degrees Celsius, this is at 20 degrees Celsius, and this is at 30 degrees Celsius. So we understand that heat always flows from higher temperature to lower temperature. So from here it should start flowing. This is H2 and this should be the H3. I hope this is clear. So when this is the situation, I should write it's an H1 is equals to H2 plus H3. Now when I write H, this is equals to K A T1 minus T2 divided by L. But as all roads are made up from the same material, so this K would be constant on K would be cancelled out on both the sides. They are of same dimensions, that means area of cross section and the length of the conductor is same. So if this is the situation, what I need to write is it's an only the temperature difference would be the different. So it's an 100 minus Tx. This is equals to Tx minus of 20 plus this is of Tx minus of 30. So this 100 minus Tx is equals to Tx plus Tx. This is 2Tx minus 20 minus 30. It's a minus of 50. So it's a 100 plus 50. It's a 150 is equals to 3Tx. And from this it's a Tx which is equals to 50 degrees Celsius. That's it. You did it. Great job. I hope this is clear. Is it clear? Is it clear? Are you sure? Are you sure? Do you understand this completely? Have you? Ready for the next question? Are you ready? Let's do it. Next question. Let's suppose the situation is it is something like this. This end, this is at 100 degrees Celsius, and and this end is at 0 degrees Celsius. This is the thickness which is equals to, let's say, 10 centimeter, and the cross sectional area of this road, this slab, sorry, cross sectional area of this slab is 20 centimeter square. Conductivity is equals to 5 units. It's a SI units. I hope this is clear. So what they want is that let's suppose we have put up a slab of the ice. It is just the slab of the ice which is having a mass of 30 gram, which is having a mass of 30 gram. So they want that find out time for which heat should flow so that this ice can be melted. So how will you do this? What could be done? What I understand is that heat is being flown from this, it's an 100 degree Celsius to 0 degree Celsius. Yes, because temperature difference has been maintained over this region. So this is basically a Q by T, that is equals to K into A into T1 minus T2 divided by L. This K is equals to 5 units. A cross sectional area, it's a 20 centimeter square. So this is 20 into 10 to the power minus of 4. T1 minus T2. This T1 minus T2, this is 100, this is 0, so it would be an 100. Divide by length, it's a 10 into 10 to the power minus of 2. I hope this is clear. Is it clear? So this is 10 twos are 20. This is 10 twos are 20. This is 5 twos are 10 into 10 to the power minus of 4 into 10 to the power 2 into this is a 10 to the power again 2. So this 10 to the power plus 2 and this 10 to the power plus 2 and this 10 to the power minus of 4 has been gone, and this is q by t. This is q by t. I hope this is clear. So this is q by t is equals to 10. Now this q required is what you need to do. You need to melt the ice so that this ice can be melted, and this ice is of 30 gram. So what you need to do is that this is q by t is equals to 10. This q can be written as ml by t, and that should be is equals to 10. So this 10 is equals to ml by 10. Mass, it's a 30 gram, so it should be a divide by 30 multiplied by L. It is 3.35 into 10 to the power 5 divide by 10. You need to solve this, and this many seconds would be required. This many seconds would be required to melt this complete mass. Yes, this could be solved easily. It is not that typical. It's a this is T, that would be equals to 3.35 into 3 into 10 to the power 6 divide by this is 3 this is 10 to the power 4. So this is 335 divided by 100 multiplied by 3 into 10 to the power 4 into 10 to the power 2 divided by 10 to the power 4. So it's a 335 into 3. It is just that calculation. It's a 900 plus 105, that is 1005 seconds would require to melt this mass. And for this much amount, let's look at certain quick questions. Blank is the best conductor of it: iron, copper, gold and silver. This is the best conductor of heat. How could I come to know? It's an information, but based on their K, it's a thermal conductivity. We can came to know about the base conductors or worst conductor of heat. Let's discuss the second question. Blank is used at bottom of cooking vessels because it is a good conductor of heat. Yes, copper is being used at the bottom of cooking vessels. Blank is the bad conductor of heat: iron, copper, gold, wood. Yes, wood is the bad conductor of it. So now let's discuss about the next topic, which is thermal resistance of a conductor. So first let's discuss what is thermal resistance. Let's have a look. What we understand is that this was the situation, that this is a T1, this is T2, this is a length L, and let's say this is cross sectional area A, and the conductivity is K. So when I say a heat has been flown from section T1 or from a site T1 to the T2, we used to call it as a Q by T, that is equals to K into A multiplied by T1 minus T2 divided by L. So if I call this as a heat current that we represent by H, then this could be written as this is H, and this could be written as it's a T1 minus T2 divided by L by Ka. So this is L by Ka. So this could be written as this H is equals to T1 minus T2 divided by R, where R is the R is the thermal resistor. It's a thermal resistor. Yes. So we can write something like this for the thermal resistance. Let's have a look. It's a thermal resistance of a conductor. Thermal resistance R of a conductor of length D and cross sectional A and conductivity K could be written as D by Ka. I have shown you because there might be certain confusion that how this D by K arrive. It is arrived by this. It's an L by K because I have chosen L as the length, and here it has been written D is the length. Now the heat current Q by T is taken as I, so that if I write I is equals to theta 1 minus theta 2 by R, it is does exist, a heat current does exist because of temperature difference. So this is Q by T into bracket Ka theta 1 minus theta 2 by T. Here the temperature difference is identical to the potential difference V of a conductor. Yes, you have learned in the 10th class something like this, that this was a V1, this was a V2, resistance R is there, and the current is flowing such as I is equals to V by R. So if potential difference is there, this electric current will flow. Same as heat current will flow until there is a temperature difference. So if temperature difference is zero, that means heat current will stop. It is something like this. So so I have represented this as a heat current. Let's call it as an H. This is equals to theta 1 minus theta 2. Does it clear does it clear Are you sure? Are you sure? Do you understand this completely? Any doubts? Any doubts up till now? Is there anything? Is there anything? Are you sure? Great. Now, let's look at the situation. That the situation is something like this. First, second, third, fourth, and onwards. Let's say this is first slab, second slab, third slab, fourth slab, and nth slab. Here this is the temperature T1, here this is the temperature T2. So as you can see that every slab, first, second, third, fourth, and onwards, each slab are connected in series. So this end is maintained at T1, this end is maintained at T2. So the total resistance R could be written as R1 plus R2 plus R3 up to Rn. When I write R, let's understood that this is D1, this is D2, this is D3, this is D4, and up to Dn. So the total uh, R equivalent, that means the total system contains a length which is equals to, because R is equals to D by Ka. Please keep this in mind. Please keep this in mind that R is equals to D by Ka, and this R could be written as D1 plus D2 plus D3 up to Dn, divide by K equivalent into cross sectional area A, because cross sectional area is same for each one. So this could be written as D1 by K1A plus D2 by K2A plus D3 by K3A up to Dn by Kna. When I write this, it's an A has been lost, And when this has been lost, this is d1 plus d2 plus d3 up to dn divided by k. This is equals to d1 by k1 plus d2 by k2 plus d3 by k3 up to dn by kn, where where k is the equivalent thermal conductivity of series combination. So when certain slabs have been connected in series, I can use this relation directly. But for this there that you need must ensure that these blocks are connected in series. Now discuss this same thing. Let's discuss the same thing for just two slabs. It is something like this, that T1 is maintained over here, T2 is maintained over here. This is a D1 and this is a D2. This is a K1, this is a K2. I hope this is clear. So for two slabs I can write it's a d1 plus d2 by k. This is equals to d1 by k1 plus d2 by k2. And from this, if I solve this, I can have this relation. It's a k is equals to k1 k2 into bracket d1 plus d2 divided by d1 k2 plus d2 k1. Now if the situation is that d1 is equals to d2 is equals to d, if their lengths are equal, then I could write it's a d1 equals to d2, then this k is equals to 2 k1 k2 divided by k1 plus k2 plus, please do remember this relation, because this is going to help us in many times. Please remember this. One more thing, when d1 equals to d2 equals to d, so this could be written as n divided by k average is equals to 1 by k1 plus 1 by k2 plus 1 by k3 up to 1 by kn. This is not to be written as average, this is equivalent. So this is the situation if all the lengths are equal. If it is the case, then this is n by k equivalent is equals to 1 by k1 plus 1 by k2 plus 1 by k3 up to 1 by kn. Have you got this? Have you? Do you understand this completely? Have you? Do you understand this? Are you sure? Are you sure? Do you have any doubts up till now? Is there anything? Is there anything? Are you sure? Are you? Great. Now let's look at this. Suppose in this situation the slabs are connected like this. It's a theta 1, theta 2, and this is theta 2, theta 3, theta 3, theta 4, and onwards. So once q by t has been entered, it is going to leave it from this. So if this n slabs are connected in parallel, then the equivalent resistance could be written as 1 by r is equals to 1 by r1 plus 1 by r2 plus 1 by r3 up to 1 by rn. And if this is the situation, then I could write it's an k multiplied by a1 plus a2 plus a3 up to an divided by d. That would be is equals to, for individual, it's a k1 a1 by d plus k2 a2 by d plus k3 a3 by d up to kn an by d. If I solve this, it is k which is equals to k1 a1 plus k2 a2 plus k3 a3 up to kn an divided by a1 plus a2 plus a3 up to an. And if we are having only two slabs, if we are having only two slabs such that this k could be written like this, it's a k1 a1 plus k2 a2 by k1 by a2 a1 plus a2. If area of cross sections are equal, it is just k is equals to k1 plus k2 by 2, where k is the equivalent thermal conductivity in parallel combination. I hope this is clear. Is it clear? Is it clear? Are you sure? Are you sure? So can you do this? Can you? Let's have a look. Let's look at the question. The situation is something like this, that this is T1, this is T2, this is L1, this is L2, and reality this where the cross sectional areas. When I have chosen A1 A2 over here, this is A1, this is A2, and this is L1, this is L2, as you can see. So this is K1, this is K2. Now what you need to do, you need to find equivalent thermal conductivity. This is requirement, that find equivalent thermal conductivity of the given slab. How will I do this? What can be done? So first tell me, do these two slabs are are in series or in parallel? Do these two slabs are in series or in parallel? Yes, these two are in parallel. Why? Because when heat current started flowing through this, it is having an option that either it could travel from this or either it could travel from this. So if any current if any current is having an options, then it is parallel combination. I hope you got this. Forget about the name of the current, whether it would be an heat current or whether it would be an electric current or whether it would be an fluid current. If it is any current, if it is any current is having an option to flow, that I could go from this or I should go from this, then they are in the parallel combination. So this would be 1 by r is equals to 1 by r1 plus 1 by r2, while the r should be is equals to L by Ka. So this 1 by r is equals to Ka by L. So this is equals to Ka by L. It's a K1 into A1 by sorry, it's a K1 A1 by, let's say this is the L1 and L2, but L1 equals to L2 is there. So this is equals to K1 A1 plus K2 A2 divided by 2L. This is equals to K1 A1 by L plus K2 A2 by L. This L has gone, and from this you could have the K equivalent. I hope this is clear. So you could write like this, it's a K equivalent which is equals to A1 plus A2 by 2. This is equals to K1 A1 plus K2 A2. I hope this is clear. Is it clear? From this you can find out this K equivalent and things will be done. I hope this is clear. Is it clear? Is it? Are you sure? Are you sure? Correct. Let's work for the next question. This is very interesting question. Understood this very detailed manner. Have a look at this. Let's suppose the situation is something like this, that these two roads are there and these two are the identical roads, that this is K, this is K, this is at 100 degrees Celsius, this end is at 0 degrees Celsius, this is length L, even this length is at L. So this is the situation. Initially this was the situation. Now onwards they have kept like this. Yes. So in this situation the this was at 100 degrees Celsius, this end is at 0 degrees Celsius. Slabs are the same, so K would be the same. Definitely length and cross sectional area will be the same. So if this is the second situation, they will say that if 100 joule of energy is being passed per second in in first configuration. Find out per second energy transferred in second configuration. So this was the situation. What they have done is that at one of the end they have kept 100 degrees Celsius. At another end they have kept 0 degrees Celsius. And these two rods were connected in series. And in this situation 100 degrees Celsius and 0 degrees Celsius. So the temperature difference is same. Temperature difference is same. But now these two slabs are connected in parallel. So, if I look at this situation, I could understand it that this I is equals to theta 1 minus theta 2 by R, or this should be written as H. This should be written as H, heat current, I should say this. And as it is per second, then this could be written as that it's an 100 joule per second. And let's call this resistance as an R. This resistance as an R because it is made up from the same material and every dimensions are same. So this could be written as H1 is equals to theta 1 minus theta 2 divided by 2R. And when this theta 1 minus theta 2, it's an 100 by 2R, this is equals to H1. Now in the second configuration, this H2 is equals to theta 1 minus theta 2 divided by R equivalent. And when I write it's an R equivalent, it is R by 2. This is H2. So this H2 is equals to 2 into theta 1 minus theta 2. It's an 100 divided by R. I hope this is clear. Is it clear? Is it clear? Are you sure? Now, they have given one more thing. They have given the H1. It's an 100 joule of energy. So this is 100 is equals to 100 divided by 2R. This has gone. And from this 2R is equals to 1. R is equals to 1 by 2. So this is 2 into 100, which is 200 divided by R. R is equals to 1 by 2. So this is equals to 400 joule of energy per second. It's a heat current. It's a 400 joule of energy per second being transferred from one end of the road to the other end. Have you got this? So this is the application of the series and parallel combination of the slabs. Please do not only learn the formula and do not only mug up the formulas. Please also be capable enough to use it, because these are the formulas to use it. These are not the formulas only to learn this. Yes, great. So let's look at certain quick questions. The dimensional formula for thermal resistance. Dimensional formula of thermal resistance. It's an R which is equals to L by Ka. And let's, L is the length. It's a meter. For the K I need to do this. It's a Q by T is equals to Ka delta T by L. So for the K this is joule per second into meter divided by meter square into 1 by Kelvin. So this meter square has gone. So this is equals to for the K into a K, it's a joule per second into 1 by meter into Kelvin. So and multiplied by A, which is meter square. So this meter is gone, this meter is gone, this gone, and this is equals to second into Kelvin divided by joule. Now you can replace it by kg meter square per second square, and the remaining task can be done. It would be an m minus 1 L minus 2 T minus 3 into K. I hope this is clear. Is it clear? Is it? Are you sure? Great. So let's just wind it up this session over here. This was all about the convection and the conduction. A convection is a theoretical session, yes, so which is having a very less probability to be asked in the competitive examination, as well as if you go through the previous year asked questions, you will find a very few questions related to the convection. But heat transfer through conduction has a vast applications, and as it is having a very vast application, it is having very high probability to be asked in different competitive examinations. So please practice a lot this kind of questions. Please practice a series and parallel kind of slaps. This will help us to get it done within a time with minimum error. Thank you, have a good day, take care, bye.